you ever looked at a new airplane and wondered why it costs hundreds of millions, sometimes billions of dollars? Well, a huge piece of that puzzle comes down to the individual parts. And these aren't just any parts. They're some of the most incredibly complex and expensive things we know how to make. So let's get into it and figure out exactly why aerospace parts cost an absolute fortune.
I know, it sounds kind of crazy, right? A tiny little bolt causing all that trouble? But it's the absolute reality of an industry where the stakes couldn't be higher. You see, every single component, no matter how small, carries this immense weight of responsibility.
And this right here? This is the core belief, the non-negotiable rule of the entire industry. Every part, from a massive landing gear strut to the smallest screw, has to work perfectly. Not just once, but every single time, under the most extreme conditions you can imagine, for thousands and thousands of hours. There are just no do-overs at 35,000 feet.
Okay, so that brings us to the fundamental problem that every aerospace engineer wakes up thinking about. They are in a constant battle with a paradox, one that's dictated by the laws of physics itself.
It really is a constant, high-stakes balancing act. On one side, a part has to be unbelievably strong to handle all the forces of flight. But on the other side, if you make it too heavy, the plane either guzzles fuel, or worse, it can't even get off the ground. The perfect part lives right on that razor's edge between being too heavy and being too weak.
So how do you solve this impossible strength versus weight problem? Well, you invent a new generation of what can only be called supermaterials. And believe me, this isn't the kind of metal you'd find at a hardware store. These are cooked up in labs specifically for the insane demands of flight.
We're talking about some amazing stuff here. You've got your advanced aluminum alloys. They're kind of the versatile workhorse of the industry. Then you have titanium, which is just legendary for its raw strength and how well it handles scorching temperatures. And of course, carbon fiber composites, which give you this almost unbelievable jaw-dropping strength in a package that's shockingly light.
Okay, so we've got our super materials. Problem solved, right? Well, not so fast. This actually creates the next huge challenge. You see, the very thing that makes these materials so strong also makes them incredibly, notoriously difficult to shape and work with. For the most part, the answer is CNC machining. The easiest way to think about it is like a super precise robotic sculptor. You feed it a digital design and it just carves that exact shape out of a solid block of metal with a level of accuracy no human could ever hope to match.
So, almost every part starts its life looking something like this. Just a simple, solid block of raw metal, what they call a billet. It's heavy, it's clunky, and it looks nothing like the finished product it's about to become.
And then, after hours, sometimes even days, locked inside a CNC machine, that block transforms into this, a beautiful, complex, and precisely engineered component. This whole process is called subtractive manufacturing, for the obvious reason that you're subtracting or removing material to get to your final shape.
And this journey from that raw block to a finished part is just mind-bogglingly complex. I mean, look at this flow chart. It's not just one step. A single part goes through receiving, drilling, machining, and then a whole gauntlet of inspections, special treatments, cleaning, painting, you name it. Every single one of those steps adds time, it adds cost, and it adds another chance for something to go wrong. Now, when we talk about composites like carbon fiber, it's a totally different ballgame. Instead of carving material away, you're actually building the part up one super thin layer at a time. This is what's known as an additive process. The old school way was to do this all by hand, which was painfully slow and, get this, created a scrap rate of up to 30%. Automation has totally changed everything. And in the world of automation, you've got two main players. On one side, there's automated tape laying, or ATL. It uses these really wide tapes of material, so it's perfect for making huge, relatively flat things, like the skin of a wing. Then you have automated fiber placement, or AFP. It uses much narrower strands, which lets it build these incredibly complex, curvy shapes with almost no waste. It's pretty amazing.
So you've got these incredible materials, and you're using these super advanced manufacturing techniques. But how does that all add up to the frankly staggering price tag for just one part? Okay, let's break down the economics of perfection. You know what? Let's just use titanium as our example. It's famous for being one of the most expensive materials out there, and the reasons why it's so pricey really tell the story of the whole industry. It all starts right at the beginning, with the raw material itself. To get titanium, you have to dig it out of the ground as mineral ore. So let's say we start with 11 kilograms of this raw ore. Well, after you put it through a really complex and energy-hungry refining process, that 11 kilograms of rock gives you just 1 single kilogram of usable titanium metal. Think about that. A huge chunk of the cost is baked in before you've even started to make anything.
But oh, it gets so much more expensive once you try to actually cut it. Titanium is so tough that it just shreds the cutting tools you use on it. It's also terrible at conducting heat, so you have to machine it really slowly, and you have to blast it with high-pressure coolants the entire time. All of that adds a ton of time and money to the whole process. And that brings us to the biggest hidden cost of all, waste. Just look at this example for aluminum, which is way more common than titanium. To get just 100 finished parts, more than 46,000 kilograms, that's 63% of the starting material, ends up as scrap shavings on the factory floor. That is an insane amount of expensive metal that you paid for, but will never fly. So after all this intense manufacturing, we get to the final and, honestly, the most critical cost of all, the absolute demand for total safety. With millions of parts being made by thousands of suppliers all over the world, how in the world do you guarantee that every single one is perfect?
Yeah, this quote from Pico MES really says it all, doesn't it? The fallout from just one bad part is so unbelievably severe that the industry has to pour massive resources into systems that prevent it from ever happening.
The industry's answer to this is something called digital traceability. Basically, it's like creating a digital passport for every single part. It tracks everything, where the raw material came from, which person worked on it, which machine cut it, every inspection result. It's a complete digital life story for every component.
And if you think this is all just theoretical, it's not. Look no further than the 2024 Alaska Airlines incident where a door plug blew out in midair. Investigators now believe that 4 critical bolts were taken out during assembly and just never put back in. A solid traceability system is designed to catch exactly that kind of human error before it can become a disaster. So when you add it all up, from the impossible materials to the precision manufacturing to a system of total digital accountability, every single step adds cost. But it's that very cost that keeps us all safe when we fly. And it leaves us with one big question. As our materials get even stronger and our designs get even more complex, what's going to be the next big breakthrough that builds the future of flight?